Hello everyone, and welcome back to Applications of Derivatives. So for this next section here, we're going to be looking at what the second derivative can tell us about the graph of a function. Last section was all about the first derivative and what it can tell us. This section is all about the second derivative and what it can tell us about the graph of a function. So we're going to get into this concept called concavity. Concavity is how a function curves or turns. Concavity has nothing to do with increasing or decreasing, but it has to do with how the function is actually curving. So if the function curves down, it is said to be concave down. If a function curves up, it is said to be concave up, like a cup. So in this little picture here, this part in blue, the function is curving downward, so the function is concave down. And in this next part, this part that's highlighted in red, this is curving upward, so it is concave up. Notice how concavity has nothing to do with increasing or decreasing, it's just how the function's curving. Now this point in between them is highlighted in green for a reason. This point is where concavity switches, and this point where concavity switches, I'm going to give it its name now, is called an inflection point. An inflection point is where concavity changes, and I'm going to give you a more formal definition later. And we're going to get into how to find these types of points in a little bit. Now the formal definition of concavity, which remember I'm not going to ask you to ever recite a definition, but the actual formal definition of concavity will give us a sense of what we need to be doing in order to figure out where a function is concave up and down. So a function is concave up if y prime is increasing, which is interesting. The function is concave up if the first derivatives are increasing. The rate of change of a derivative, the derivative of a derivative, that is called the second derivative. So concavity is going to be tied with the second derivative. The second derivative tells us all about the concavity of a function. So then a function is concave down if y prime is decreasing. And here's the actual definition of an inflection point, which, while I'm not going to ask you to recite it, you will have to use the definition of an inflection point a lot. So if f is continuous at some point x equals c, and if f changes concavity at c, if it switches from concave up to concave down, or vice versa, then you have an inflection point at x equals c. So inflection points are where concavity changes. So for this next one, we're just going to look at this graph and we're going to identify where this function is concave up and down, and just by looking at a graph, we're going to find the inflection points. Now, sometimes inflection points, like in this graph here, are going to be super obvious and super easy to see just by looking at it. I will say, though, that not every inflection point is going to be super obvious. Some inflection points are going to be very subtle and not easy to see from a graph. So that is why we're going to be using second derivatives primarily to figure out where the inflection points are, because they're not always visible from a graph. However, for this example, they are going to be. So let's go from left to right. So for this first part of the graph here, see how it is curving slightly downward? That means it is concave down. Now I do want to point out that inflection points are actual points, which means the point needs to actually be defined. An inflection point is a defined point. So asymptotes are not considered inflection points. Even if concavity switches on either side of an asymptote, it doesn't matter. An asymptote cannot count as an inflection point. So then, after this asymptote, the function starts to curve slightly up. So since it's curving slightly up, we say that it is concave up. Then it looks like about right after negative pi over 2 here, the function then starts to curve down. So since it's curving down, it is concave down. Now that point right there at negative pi over 2, where concavity changed. Since concavity switched on either side of negative pi over 2, that means negative pi over 2 is an inflection point. And like I said, in a graph like this, inflection points are really obvious. In a lot of graphs, they're not. So then again, at x equals 0, this is not an inflection point. It is an asymptote. So after the asymptote, it goes back to curving slightly up, so it's back to concave up. Looks like we've got another inflection point at pi over 2. And then after that, it goes back to curving downward, so it is back to concave down. And you get the idea. It's concave up again after this asymptote. We've got another inflection point here at 3 pi over 2. And then it goes back to concave down. Then we jump over this asymptote, and it is back to concave up. By the way, I think the subtitles keep thinking that asymptote is ask him to. I'm sorry. I'm doing the best I can with the technology. Now, we're not always going to be using a graph to identify where a function is concave up and concave down. We're going to be using the second derivative to actually test to see where a function is concave up and where a function is concave down. So make sure that you write these down because you're going to be using these tests for concavity all the time. So if the second derivative, f double prime, is positive on a particular interval, then the function is concave up. So if the second derivative is positive, the function is concave up. If the second derivative is negative, then the function is concave down. And if you have a point x equals c and the second derivative changes signs at x equals c, then you have an inflection point. So inflection points occur where the second derivative changes signs, either from positive to negative or vice versa. Now, how to actually find inflection points without a graph? Inflection points occur where either the second derivative equals 0 or where the second derivative is undefined. Sort of like critical points, except it uses the second derivative. So to find potential inflection points, you're going to find the second derivative, you're going to figure out where it equals 0, and where it is undefined. Now, remember how not every critical point was a local min or max? The same thing is going to apply here. Not every point where the second derivative equals 0 or is undefined is going to be an inflection point. You actually have to make sure that the second derivative changes signs on either side of that point. And we really don't have a better name for these type of points, so we'll just call them potential inflection points. So here's an illustration of that. So this point here is where the second derivative equals 0. And the function switches from concave down to concave up, so this is absolutely an inflection point. The second derivative equaled 0 and concavity switched. However, I know this next graph's a little hard to see, but it does kind of flatten out here in the middle, so the second derivative is actually equal to 0 here. However, concavity does not switch on either side of that point. It goes from concave up back to concave up, so because concavity did not switch on either side of this point, it is not an inflection point. Same thing here. So this first point over here on the left, It's a vertical tangent. Vertical tangents mean the first derivative is undefined. If the first derivative is undefined, that means the second derivative is undefined. So right here, the second derivative is undefined, and concavity switches from concave up to concave down. So it's an inflection point. However, at this sharp point where neither the first derivative nor the second derivative are defined, so the second derivative is undefined here at that sharp point, concavity did not switch. It went from concave down back to concave down. Because concavity did not switch, it is not an inflection point. So, moral of the story is inflection points occur where the second derivative equals 0 or where the second derivative is undefined. However, to make sure that they are inflection points, you have to look at the sign of the second derivative on either side. You have to make sure that the second derivative changes signs and that concavity does switch. If concavity does switch on either side of those points, then they are inflection points. So we're going to take this function and we're going to identify where the function is concave up and where the function is concave down. And while we're at it, we'll be able to locate the points of inflection. So concavity and inflection points have to do with the second derivative. So let's find the second derivative. So we got to start with the first derivative. F prime of x is equal to 12x cubed minus 12x squared minus 12x plus 12. And then we're going to go find the second derivative. So the second derivative, which is the derivative of the derivative, is going to be 36x squared minus 24x minus 12. So inflection points occur where the second derivative equals 0 or where the second derivative is undefined. We don't have to worry about where the second derivative is undefined, so we're just going to figure out where the second derivative equals 0. So the first thing I'm going to do is I'm going to make my number smaller by taking out a greatest common factor of 12. Gives us 3x squared minus 2x plus 1. And I'm going to set it equal to 0, and I'm going to solve for x. So when you factor this, this is going to factor as 3x plus 1 times x minus 1. So then we're going to get two potential inflection points. So set 3x plus 1 equal to 0, and we get x equals negative 1/3. Then set x minus 1 equal to 0, and we get x equals 1. There's no better name for them, so I'm going to just call these potential inflection points. To figure out whether they are inflection points or not, we're going to have to look at the sign of the second derivative on either side of these. And just like we did with critical points, I'm going to draw a number line. Now this time, this number line is going to represent the second derivative because we're working with concavity. So I am going to label it as f double prime, with positive infinity on this side and negative infinity on this side. And it's going to be basically the same idea like we did with the first derivative with increasing and decreasing. This time we're going to put our two possible inflection points on the number line, so negative 1/3 here and positive 1 here. And I'm going to pick test points in each of these intervals, and I'm going to plug the test points into the second derivative to figure out whether the function is concave up or concave down. So we have the interval from negative infinity to negative 1/3. Let's pick a test point in that interval. Do not use negative 1/3. Use something else, like let's say negative 1. And I'm going to plug negative 1 into the second derivative. So when you plug negative 1 into the second derivative, it is positive. So the second derivatives are all positive on this interval. Then I'm going to pick a test point between negative 1/3 and 1. A good one to use is 0, and I'm going to plug 0 into the second derivative. So when you plug 0 into the second derivative, you get a negative number. Because your test point came out negative, that means all of your second derivatives are negative on this interval. Then we're going to pick a test point on the interval from 1 to infinity. A good point to use is, let's say, 2. And we're going to plug 2 into the second derivative, and remember, all you care about is whether it's positive or negative. So when you plug 2 into the second derivative, you get a positive number. Because your test point came out positive, that means all of these second derivatives are positive on this interval. So let's actually tie this all together and figure out where the function is concave up and where the function is concave down. Remember, if the second derivative is positive, that means the function is concave up. So the function is concave up on this interval here, and is concave up again on this interval here. Then it is concave down right here between -1/3 and 1. So let's actually put these together in what are called intervals of concavity. So this function is concave up on two separate intervals. On the interval between -infinity and -1/3, and we're not going to include -1/3 because it's neither concave up nor concave down at that point. And then it is concave up again on the interval from 1 to infinity. Then this function is going to be concave down. I'm sorry, it's glitching again. It is going to be concave down on the interval between -1/3 and 1. Now for the inflection points occur where concavity switches. Come on, there we go. So the inflection points at -1/3, concavity switched from concave up to concave down, so -1/3 is an inflection point. Then over here at 1, the function switched from concave down to concave up, so since concavity switched on either side of x equals 1, that means it is an inflection point. So we're going to be taking a look at this next function here, sine inverse of x, on the open interval -1 to 1, and we're going to figure out where the function is concave up and concave down, and we're going to locate any points of inflection. So concavity deals with the second derivative, so let's actually find the second derivative. So we're going to start with the first derivative. You might remember that the derivative of sine inverse is 1 over the square root of 1 minus x squared, which, since we're going to need to take its derivative, I'm going to rewrite this as 1 minus x squared to the power of -1/2. So then for the second derivative, we're going to use a whole lot of chain rule to find the second derivative. So the outside function is the power of -1/2. The inside function is 1 minus x squared. So the derivative of the outside, we're going to move down the power, leave the inside alone, and decrease the power by 1. -1/2 minus 1 is -3/2. Then we're going to multiply it by the derivative of the inside. The derivative of 1 minus x squared is -2x. Now remember, the moment that you see negative exponents, you do have to start thinking variables in the denominator, and we are going to be dealing with the potential that the derivative is undefined. So just going to simplify this a little bit more. First of all, -1/2 times -2 is +1, so that cancels out. X is left in the numerator, and I'm going to move this 1 minus x squared to the -3/2 into the denominator. So we're going to get a 1 minus x squared to the power of 3/2 in the denominator. Now, the function, we're not dealing with all real numbers here. we are only dealing with the open interval -1 to 1. So that means that -1 and +1 are not included in the domain, and it's not asking for concavity at those points. So if -1 or 1 come up as a potential inflection point, we get to ignore them because they're not going to be included in this. So when we have a fraction is equal to 0 when the numerator equals 0. So that means the second derivative is going to equal 0 when the numerator is equal to 0. Now, for the denominator, the second derivative is going to be undefined when the denominator equals 0. However, the only points that make the denominator equal 0 are 1 and -1, which are not included in the domain, so we get to ignore them. So x equals 0 is our only potential inflection point. So to figure out whether this actually is an inflection point, we're going to draw another number line. And this number line is going to represent the second derivative. We're going to put our potential inflection point on the number line, and that broke up this into two intervals. Now, here's the thing. Number lines go from -infinity to infinity. However, we do have to keep in mind that we're really only looking between -1 and 1. So I'm going to kind of block it off here at -1, and I'm going to block it off here at +1. Which means really the only two intervals that we are looking at are the intervals between -1 and 0 and the intervals between 0 and 1. So yeah, we are going to have to pick a couple of fractions. We are going to have to keep in mind that we cannot use 0, and since this is an open interval, we cannot use -1 or +1. So let's pick a test point in this first interval. A good test point to pick between -1 and 0 is, let's say, -1/2. And let's plug -1/2 into the second derivative, and all you care about is whether it is positive or negative. So if you plug in -1/2, you get a negative number. If the second derivative is negative, that means the function is concave down. Then we're going to pick a test point on the interval between 0 and 1. A good test point to use is, let's say, +1/2. So let's plug +1/2 into the second derivative and see what we get. And when you plug in +1/2, you actually get a positive number. If the second derivative is positive, that means the function is concave up. So let's actually write those as intervals of concavity. So this function is going to be concave up on the interval from 0 to 1. 0 is not included because it's neither, it's not concave up or down at 0, and 1 was not included in the original domain, so we're going to give it a parenthesis. So then this function is going to be concave down on the interval from -1 to 0. So at 0, concavity clearly switches at 0. At 0, the function switches from concave up to concave down. So x equals 0 is an inflection point. So for this next one, let's say that you have a function, and I've already gone ahead and found the second derivative for you. We're going to figure out where this function is concave up and concave down, and we're going to determine the points of inflection of this function. So right away, remember, inflection points occur where either the second derivative equals 0 or where the second derivative is undefined. And when your second derivative is a fraction, remember that a fraction is equal to 0 when the numerator equals 0, and a fraction is undefined when the denominator equals 0. So let's start with where the second derivative is going to equal 0. So f double prime equals 0. when the numerator, 3x squared plus 4 equals 0. Now, if you take a look at this, this doesn't have any real solutions, so it's not equal to 0 anywhere. So then the second derivative is undefined when the denominator, x squared minus 4 to the third power, is equal to 0. So, take the cube root of both sides. We get x squared minus 4 equals 0. Gives us two potential inflection points. We get x equals 2 and x equals negative 2. Remember, these are potential inflection points. We don't know if they actually are inflection points yet, not without looking at the second derivative sign on either side of these points. So let's make another number line. This number line is going to represent the second derivative with positive infinity over here and negative infinity over here. And we're going to put our two potential inflection points on this number line, so negative 2 here and positive 2 here. And we're going to pick test points in each of these intervals, and we're going to plug them into the second derivative. Remember, if the second derivative is concave up, if the second derivative is positive, it is concave up. If the second derivative is negative, it is concave down. So let's pick a test point in this interval. Let's say negative 3. So let's plug negative 3 into the second derivative. So if you plug negative 3 into the second derivative, the numerator, 3 times negative 3 squared plus 4 is going to be a positive number, times 10 is a positive number, so the numerator is always going to be positive. And then we have negative 3 squared, which is 9, minus 4, which is a positive number, cubed is a positive number. So if the second derivative is positive, this function is concave up. Next, let's test 0. So let's test a test point between negative 2 and 2, like let's say 0, and plug it into the second derivative. So the numerator, still always positive. 0 squared minus 4 is a negative number. A negative number cubed is negative. So the second derivative is negative. If the second derivative is negative, that means it is concave down on that interval. Then a good test point to pick between 2 and infinity is, let's say, 3. So we're going to take 3 and we're going to plug it into the second derivative. So again, numerator is always positive. Then in the denominator, 3 squared is 9, 9 minus 4 is 5, 5 cubed is a positive number. If the second derivative is positive, that means the function is concave up. So let's find the intervals where it's concave up and concave down. So it is actually going to be concave up on two separate intervals. One of them is between negative infinity and negative 2. And the other one is between 2 and infinity. Then this function is going to be concave down on the interval negative 2 to 2. And for inflection points, there are two of them. Remember, inflection points are where concavity switches. So at x equals negative 2, the function went from concave up to concave down, so x equals negative 2 is an inflection point. Then at positive 2, the function went from concave down to concave up, so x equals positive 2 is also an inflection point. Now, the second derivative test is a test where you can use the second derivative to figure out whether a critical point is a local minimum or a local maximum. So your critical point is x equals c. So if you plug x equals c into the second derivative and you get a positive number, that means the function is concave up at x equals c. Well, concave up, as I just illustrated, that means this is a local minimum. So if you plug a critical point C into the second derivative and you get a positive number, that means it's concave up, which means you have a local minimum. Now, if you take your critical point and you plug it into the second derivative and you get a negative number. If the second derivative is negative, that means it is concave down. So at your critical point, if the function is concave down, that means that's a local maximum. So the second derivative test is actually, when it works, really easy and fast to use, because all you have to do with your critical points are plug them into the second derivative and see whether the second derivative is positive or negative. If the second derivative is positive, you have a local minimum. If the second derivative is negative, you have a local maximum. So the second derivative test has its advantages and its disadvantages. One advantage of the second derivative test is it can be really fast and easy to use. One disadvantage is it involves finding the second derivative. So sometimes finding the second derivative is a lot of work. Another disadvantage with the second derivative test is it is possible for it to be inconclusive. So if you take your critical point and you plug it into the second derivative and you get 0, that means the test is inconclusive. You might have a local max, you might have a local min, you might have neither, you have no idea. So again, that is one big disadvantage of the second derivative test, is that it can be inconclusive. If your second derivative test is inconclusive, you just have to use the first derivative test instead, which, as you saw, never fails you. Let's actually use the second derivative test, because while I do leave it mostly up to you which test you use, let's see the second derivative test actually in action. So we're going to take this function. Now, I've already gone ahead and found the first derivative. So first derivative is 4x cubed minus 12x squared. We're going to find the local extrema of this function here, and we're going to figure out the intervals on which it is increasing and where it is decreasing. So local extrema and increasing and decreasing, both of those are going to involve using the first derivative. First derivative deals with increasing and decreasing and local maxes and mins. Then for parts C and D, we're going to find where the function is concave up and where it's concave down, and identify the inflection points. Inflection points and concavity, both of those have to do with the second derivative. So for parts C and D, we're going to use the second derivative. So let's start with where the local extrema occur. That means finding critical points. So let's find our critical points first. So our critical points are going to occur where the first derivative, 4x cubed minus 12x squared, is either equal to 0 or where it is undefined. Since this is a polynomial, we just have to worry about where the first derivative equals 0. So I'm going to factor out a 4x squared out of both of these terms. Gives me x minus 3. Gives me two critical points. X equals 0 and x equals 3. Remember, not every critical point is a minimum or a maximum. So to figure out exactly what these are, we're going to draw a number line to represent the first derivative. And we're going to put each of our critical points on that number line. And because I'm going to have two number lines, I am going to make sure that I label this as f prime. And I'm going to put my critical points 0 and 3 on the number line, and I'm going to pick test points in each of these intervals and plug them into the first derivative and see whether they are positive or negative. So if you pick a test point between negative infinity and 0, like let's say -1, plug -1 into the first derivative and you get a negative number. So because the first derivative is negative, the function is decreasing. Then you're going to plug a point between 0 and 3 into the first derivative, like let's say 1. If you plug 1 into the first derivative, you actually get a negative number again. So if the first derivative is negative, the function is decreasing. And then Plug a test point between 3 and infinity, like let's say 4, into the first derivative, and you're going to get a positive number. If the first derivative is positive, that means the function is increasing. So for your intervals of increasing and decreasing, it is actually increasing on 2 intervals. And remember, you cannot lump these together as negative infinity to 3. It is neither increasing nor decreasing at 0, so you do need to write them separately because it does break apart at 0. So do not just combine it into negative infinity to 3. Your intervals of increasing are from negative infinity to 0 with a parenthesis, and then again from 0 to 3. Then the function is, this is decreasing. I started with decreasing. Then this function is increasing on just one interval from 3 to infinity. Sorry about that. And right away, we can identify at least a local minimum. So x equals 3, the function goes from decreasing to increasing, so x equals 3 is a local minimum. Now, x equals 0, while a critical point, is neither a local min nor a local maximum. At this point, we don't really know what it is. It's neither. So next, let's jump into parts C and D. Concavity and inflection points both have to do with the second derivative, so let's actually find the second derivative. So the second derivative is going to be 12x squared minus 24x. So then let's find our potential inflection points. Our potential inflection points occur where the second derivative is either equal to 0 or where the second derivative is undefined. We don't have to worry about where the second derivative is undefined, so we'll just have to worry about where the second derivative equals 0. So I'm going to factor out a 12x, gives me x minus 2, and I'm going to set this equal to 0, and I'm going to solve for x. So I'm going to get 2 potential inflection points, x equals 0, and x equals 2. Remember, there's no real better name for these. They're just potential inflection points. Oh, goodness gracious. That is potential inflection points. I don't know what is going on with this. I'm sorry about that. Anyway, to figure out whether they actually are inflection points and to find the intervals of concavity, I'm going to draw another number line, and this time this number line is going to represent the second derivative. So negative infinity on this side, infinity on this side. I'm going to put my 2 potential inflection points on this number line, so 0 here and 2 here. And I'm going to plug test points from each of these intervals into the second derivative. If the second derivative is positive, it is concave up. If the second derivative is negative, it is concave down. So plugging in a test point between negative infinity and 0, like let's say negative 1, plug it into the second derivative and you actually get a positive number. If the second derivative is positive, that means it's concave up. Plug a test point between 0 and 2, like let's say 1, into the second derivative, you get a negative number. That means it is concave down on this interval. Then pick a test point between 2 and infinity, like let's say 3, plug it into the second derivative, you get a positive number, so it is back to concave up. So let's actually write out our intervals of concavity. So it is going to be concave up on 2 separate intervals from negative infinity to 0, and then again from 2 to infinity. I'm sorry, this is completely illegible and I don't know how to fix it. Between 2 and infinity. Then the function is concave down on the interval from 0 to 2. Now for your inflection points, there's 2 of them. Concavity switched on either side of 0, so x equals 0 is an inflection point. And concavity switched again on either side of 2, so x equals 2 is also an inflection point. So for this next one, what we're going to do is we're going to actually use the second derivative test to find the local extrema. I know for the last one we used first derivative test because we needed to use it anyway for increasing and decreasing, but this time I'm going to show you what the second derivative test looks like and how easy it can be. So we've actually used this exact same function before and we've already found its second derivative, and its first derivative. We found its first and second derivatives already, and we found its critical points. So the critical points from the last time that we worked with this exact same function, remember, critical points occur where you set the first derivative equal to 0. You get 2 critical points. We got x equals -1 and x equals 1. And we also found that the second derivative, you can use the factored version, unfactored version, it really doesn't matter. 12 times x minus 1 times 3x plus 1. So here's how the second derivative test works. You're actually going to take your critical point as is and plug it directly into the second derivative. So if you take the second derivative and you evaluate it at, let's say, -1, you get 48, which is clearly a positive number. Since the second derivative is positive, that means this function is concave up. Concave up looks something like this. That point right there is a local minimum. So right away, you know that x equals -1 is a local minimum. And since we use the second derivative, this is by the second derivative test. SDT is a completely acceptable shorthand. So, second derivative test, when it works, is really fast and easy to do because you just plug your critical point directly into the second derivative. If it's concave up, it's a local minimum. If it's concave down, it's a local max, and that's it. Now, here's the problem with the second derivative test. If you actually plug in +1 into the second derivative, you get exactly 0. Remember, if you get a second derivative equal to 0, the second derivative test is inconclusive. When the second derivative test is inconclusive, what you're going to do is use the first derivative test instead. If you use the second derivative test, it's neither a maximum or a minimum. We found this already. So that is one issue with the second derivative test, is that it can be inconclusive. So for this next one, we're going to take this function, and without a graph, we are going to use calculus to find the local extrema of this function. Now, if you're ever asked to find the local extrema, you can really pick whether you use the first derivative test or the second derivative test. It really doesn't matter what test you use. You do need to start this off the same way, though. Local extrema, local mins and maxes, occur at critical points. So the first thing that we have to do is we have to actually find the critical points. Critical points are when the first derivative either equals 0 or where the first derivative is undefined. So we're going to find the first derivative. So the first derivative, move down the power, decrease the power by 1, we get -15 x to the 4th, and then we have plus 15x squared. So then we're going to take this derivative. I'm going to factor out a -15 out of both terms, and I'm going to factor out an x squared out of both terms. So we get positive x squared minus 1 equals 0. And then I'm going to set the first derivative equal to 0, and then I'm going to solve for x. So, setting -15 x squared equal to 0, we get x equals 0. And then you can either factor x squared minus 1 as a difference of squares, or you can take x squared minus 1, set it equal to 0, and solve for x. You actually get two other critical points. We've got x equals positive 1 and x equals negative 1. So there are 3 critical points here. That's a lot. So you can either use the first derivative test or second derivative test. It is completely up to you. First derivative test is never inconclusive, so if you just want to dive into the first derivative test, you absolutely can. I am going to show you what second derivative test would look like and show you that it can go really quickly if you used it. So to use the second derivative test, we're actually going to quickly find the second derivative. So the second derivative is going to be negative 60 x cubed plus 30x. And what I'm going to do is I'm going to plug each of these points directly into the second derivative, and I'm going to see what happens. Now, unfortunately, if you plug in 0, you get 0, so it's inconclusive. So we'll have to use first derivative test for x equals 0. It's not going to be a big deal. Next, let's plug in 1 into the second derivative. And remember, all you really care about is whether the second derivative is positive or negative. So we get negative 60 times 1 cubed plus 30 is going to be a negative number. If the second derivative is negative, it is concave down. Concave down looks something like this. That's a local maximum. So x equals 1 is a local max. By the second derivative test. So then we're going to do the same thing for x equals negative 1. We're going to plug negative 1 into the second derivative, and we're going to see if we get a positive number or a negative number. Remember, a negative number cubed is a negative, so we'll get negative 60 times negative 1, which is positive 60, minus 30 is a positive number. If the second derivative is positive, it is concave up. Concave up looks like this. That means that is a local min. So x equals negative 1 is a local min. Local min. Minimum by the second derivative test. Now for x equals 0, you are going to have to use the first derivative test. So, here's a quick little number line for the first derivative. If you plug in, don't use 1 or negative 1 because they are actually critical points. You can't use negative 1 or 1, but you're going to pick a test point, let's say, between negative 1 and 0, like let's say negative 1/2. So we get negative 15 times negative 1/2, which is going to be 7.5 plus another 7.5 gives you a negative, what the heck? Hold on, I'm having a technical problem here. I think that pen is only going to get worse. Give me 1 second, I have to pause the recording. All right, let's hope that what I did actually fixes it a little bit. Sorry about that. So if you plug in, let's say, negative 1/2 into the second derivative, you get a positive number, which means the function is increasing. And if you plug in, let's say, positive 1/2 into the first derivative, you get another positive number, which means it is increasing. So x equals 0 is not a local extrema. Apparently what I did not fix the problem. I am sorry. So this is just kind of a summary of what derivatives tell us, what the first derivative tells us, and what the second derivative tells us about the graph of a function. So First, if the first derivative is positive, that means the function is increasing, as we can see here. And you notice how concavity is not really tied to increasing and decreasing. Concavity can switch, as you kind of see here, but the function still continues to increase. So if the first derivative is positive, the function is decreasing. If the first derivative is negative, then the function is decreasing. And again, it's not tied to concavity, so concavity can switch even while a function continues to decrease. Now, if the first derivative changes signs, either from positive to negative, giving you a local max, or from negative to positive, giving you a local min, that's a local extrema. So if the first derivative changes from positive to negative, you have a local max. If the first derivative changes from negative to positive, you have a local min. Now, that's using first derivative test. If you use second derivative test, at this point up here, if the first derivative equals 0 and the second derivative is negative, means this is concave down, we have a local minimum. At local maximums, that is where the first derivative equals 0 and the second derivative is positive. Since it's concave up, it's a local minimum. And then if the second derivative equals 0, if the second derivative is positive, it is concave up. And it doesn't matter if it's increasing or decreasing. So this is an example here on the left where the function is increasing and concave up. And over here, this is decreasing and still concave up. So if the second derivative is positive, it's concave up. If the second derivative is negative, the function is concave down. So this is increasing and concave down, and this is decreasing and concave down. And at a point where the second derivative changes signs, it is called an inflection point. So if concavity switches, you have an inflection point. So that is kind of a summary of what both the first and the second derivatives can tell us about the graph of a function. So thank you all very much for watching, and what we're going to be doing in the next section is we're going to be tying this all together to actually, without a graphing calculator, draw a pretty good approximation of what the graph of a function should look like just by using first derivatives and second derivatives. So stay tuned for that. If you have any questions, please feel free to email me, and I will see you in the next video for curve sketching.